paper is from Petrenel, Stewart Whiteley. Jessica Hill gave this presentation, I think, on Monday at the EAG in Nice, and we are privileged to hear it for the second time so soon. Are you guys okay with that? All right. Okay. So, and really here we're going to talk about the opportunities of what we've learned so far to be applied in Europe and let's say near Europe. So, Stewart, over to you.
Thanks very much.
Please.
How do we do it? Just to drive the graph forward?
Yeah, you can point that way forward and that's your pointer.
Okay. Right, good morning. My name is Stewart Whiteley. I'm going to present to you the results, or some of the results from a study we've been undertaking, reviewing and quantifying and trying to rank the shale gas resource potential in Europe, North Africa and the Near East. Near East, I mean sort of Syria, Lebanon, Jordan and so on, and excluding the Middle East. The lead author on this work is really Jessica Hill. She's currently at a shale gas workshop in Nice, and we presented this together yesterday. So I've got the job of doing it today. The structure of the presentation, basically, I'll give a very brief introduction, which will be a very quick overview of the activity around the world and Europe. Then we'll go on to look at basically the critical success factors that we think are required to make a successful shale gas play. And that's drawing on all the work from the United States, of course, that Stewart has just presented. Then we'll go on to take a regional look at the selected areas. So we'll look at regionally at North Africa and the Near East. And having done that, we'll then specifically pick out a country as an example to look at in a bit more detail. And then I'll talk about the quantification of the potential resource and go on to show you some interesting conclusions on that. So, of course, production has occurred from North America only at present, and that's specifically USA, and you've obviously heard a lot about that. The interest in shale gas, of course, extended from there. It's now really a global phenomenon. And some interesting countries. I mean, Switzerland, of course, the Posidonian shales has been actively looked at, but places like Uruguay and Argentina are on the map. And the latest addition we've got is Indonesia, where there's some licenses have been issued, and we've also been looking at the potential there. That's probably more clearly shown on that map, basically. So there's a large number of parts of the world now are being actively looked at. We're going to focus in on Europe, basically, and the North African countries and the Near East. You can see there, basically, that the height of activity, or the highest activity, basically, is occurring in Poland, and we've obviously heard a bit about that. But within Europe, generally, there are other potential shale gas plays, and there's essentially three plays in the Paleozoic. So there's a Cambrian Ordovician play, which extends from the Alum shales, basically, which extends from Denmark into Sweden. There's a Silurian shales, basically, which, of course, you've heard a bit about this morning in Poland. There's a Carboniferous play, basically, that extends from the Cheshire Basin in England through to Poland. And they're notably all Paleozoic in age, and that's probably an important selection criteria. But the Jurassic, both the Upper and Lower Jurassic, are also being actively looked at. Often there's a key issue there around maturity, and some of the companies are accessing those areas basically for oil shale potential rather than gas shale potential. So, is that a bit better? Okay. So we've been studying the potential based in Europe, North Africa and the Near East. And the steps we've taken basically were initially to try and understand the critical success factors, drawing on the experiences from the States. We've then gone on to try to identify basically the prospective basins and the shales within those basins that could be potential shale gas targets. We've started basically to work our way through the countries now, quantifying the resource potential. And we started at the bottom, basically in North Africa and the Near East, and we're working our way through at the moment. So I'm going to present you some quantifications, some estimates basically we've made for North Africa. And the final step basically was to screen and try and rank the countries and the basins in terms of their opportunity, both from a technical and a commercial perspective. So first of all, the critical success factors for a successful shale gas play. We've taken a selection of those, basically, and the first one, of course, is lateral. The top there is lateral extent and thickness. And basically, having reviewed the information from the States, basically, then there's probably a minimum limit of about 50 feet in terms of a potential shale gas. Not only from a commercial perspective, but also from a frackability perspective. The other thing is you need large areas. 200 square miles, probably the absolute minimum, basically, as an incremental project, basically. Another important criteria, of course, is the total organic content. And in screening the opportunities and quantifying the resources, we've tended to try and take two TOC, API, gamma ray activity cutoffs, basically, a TOC of more than 1% and an API of around about 150 or more. The other key issue, of course, is the shales, one way or another, have to be buried into deeply enough, basically, to gone through into the wet gas window. In screening out the opportunities, basically, we've taken a different reflections value of 1% as the cutoff. So anything above that, we've included. The other important criteria, of course, is traps and seals. That's essential to retain the gas, and they could be intraformational seals, basically, or top and bottom seals. It's been touched on earlier, basically, about the importance of the mechanical properties of the rock, of course. Two key issues there. It needs to be permeable somehow, so fractures in some cases can help enhance the permeability. But I think very importantly, it needs to be brittle, basically, to be able to be fracked. And I think the Barnett Shale, for example, is something where there's some debate about whether fractures actually make a significant contribution. The important thing about the Barnett Shale is it can be fracked because of relatively high silica content. The final criteria, of course, is the commercial criteria. Mustn't forget those. Drilling costs we've heard about earlier, but of course there's also gas price, fiscal terms, and so on that are important there. Proximity to infrastructure. So they're the selection criteria we've applied. So now focusing in on a region basis, we're looking at North Africa and the Near East, and here's a breakdown of the potential organic shales, basically, within the region. So starting from the bottom, the Ordovician contains some hot shales, basically some high shales with a significant TOC, and they occur locally, basically in Algeria, Jordan as well. The principal opportunity in the region, basically, is the Silurian. It's a very regionally extensive shale, basically, where you've got high organic contents, basically hot shales from basin succession running all the way through from Morocco into Saudi Arabia and the Arabian Peninsula. There are, of course, other shallower targets, basically, where you've got hot shales in the Devonian, the Carboniferous, a bit sort of speculative there. As you step up into the Mesozoic, then there are organic-rich shales in the Mesozoic, but you start getting into issues whether they've reached sufficient maturity to have generated gas. Our focus has been primarily on the Silurian and certainly the Paleozoic as the principal organic-rich shales in the region. A very coarse and crude way of ranking the shales was to try and use a traffic light system, basically, to try and tease out basically those shales that would have the highest prospectivity. And what comes clearly out of this, basically, is that the Silurian shales probably meet many of the criteria that are required, basically, to potentially have a successful shale gas play. The Mesozoic shales and certainly the Paleogene tend to be immature or either that or buried at significant depth. So our focus has been basically looking at the Silurian, and this is a map that was published by Luning, the black shale expert, and just showing the distribution of the hot shales in North Africa and the Near East. And basically, of course, the hot shales cover present day most of North Africa. The notable exception is Egypt, basically, where because of non-deposition and erosion and Hercynian conformity, the shales are missing. In terms of the depositional environment, the hot shales, basically the base of Silurian, were deposited in a noxic event that occurred as a result of marine transgression following the glacial melting at the end of the Ordovician. And the principal thing to note there, of course, is that there was a very uneven paleo relief at the time of deposition. So you've got a characteristic of a very large variations in ranges in thickness and organic content. And that immediately means that you're into sweet spots, basically, trying to identify sweet spots that have the highest organic content and the shale gas potential. There was a subsequent event, basically, where there was some additional, the shales themselves were deposited in the Rudanian, but there was also a secondary organic rich shale in the Thalassian. In terms of the burial history of the Silurian shales in North Africa, then of course there was initial burial, uplift during the Hercynian orogeny and erosion, and then reburial during the Mesozoic and subsequent uplift in the Cainozoic. So it's gone through an interesting burial history, basically, that certainly in many parts of the area basically has pushed these shales into the gas window and then brought them up to depths which are potentially commercially exploitable. Just as one example, we've pulled out Jordan, basically. The Silurian shales are not present everywhere in Jordan. They're present basically in the eastern part of the country, in the Risha area of Jordan, and there's two producing fields in Jordan. There's the Risha gas field that sits right at the northeastern part of the country. I think there's the Hamza oil field, basically, which is a shallower Mesozoic field. But the Silurian shales basically are present over a significant part of the country. The reason for looking at Jordan, first of all, it's got limited indigenous hydrocarbon resources itself. So the only thing is really the Risha gas field. It imports gas, oil from Saudi Arabia, the United Arab Emirates, Iraq, and imports gas from Egypt. So it's short of its own hydrocarbon resources. They've been actively encouraging the development of indigenous resources, and so they're potentially encouraging fiscal terms for the development. On the technical side, then, the Silurian shale is present as a Mudwara formation, and that formation itself is thickest in the eastern part of the country, just to the west of the Risha area. There's potentially more than one hot shale horizon. In Jordan, basically, there's two hot shale horizons within the Silurian, although the basal one is the most prospective. There's also organic rich shales in the underlying Ordovician. So overall, sort of seeing the right sort of mix of technical and commercial factors. That's a typical log, basically, from the area, and just a diagram there, basically just showing the distribution of the hot shales. The basal hot shales are the primary target, or will be the primary target. And you can see they've been deposited on this very uneven paleo relief, and so you've got areas where thick shales are typically in excess of 20 meters thick, very high radioactive shales, but elsewhere where they're absent and missing. I think the important thing also to note here is that there's the API 150 gamma ray cutoff that we applied, and the shales themselves, the organic rich shales themselves, are only about sort of 15 to 30 meters thick, so it's not that they themselves are not particularly thick. There's a huge sequence of grey shales above, basically, of the order of 250 to 300 meters, and if that potentially contains gas, it could be a significant resource. It's a cross-section through Jordan, basically. The area the shales cover basically make up about 13,000 square kilometers, so it's a significant area. It ticks the box in terms of area. The depths of the hot shale are typically around about 1,500 down to 3,000 meters, so it sort of meets the commercial window in terms of depth. In terms of maturity, it tends to be a progressive increase in maturity from south to north. So as you go in towards the Risha area of Jordan, the thermal maturity is high enough basically to push all that lot into the gas window. And that, of course, partially explains why the Risha gas field is there sitting in the Ordovician. Okay, going on to quantify the shale gas resource potential in the region. Probably a good starting point is just to look at what's been done before. And the most often quoted reference is Rojner's estimates, basically, where you look back in 1997, looked at the unconventional petroleum resources in the world as a whole, of which shale gas was part of that. and came to the conclusion that there was about 16,000 TCF of potential shale gas around the world. Now those estimates themselves were quite interesting, calculated basically. They were taking oil shale rock volumes and applying a constant gas factor. So there's a potential for double counting in terms of shale gas and oil gas, and certainly no account was taken of the possibility that the shales needed to have been buried into the sufficiently deep to have gone into the gas window. But it's a rudimentary estimate, but it certainly gives an interesting benchmark. In the area we've been focusing on, so in the North Africa and the Near East, the nearest estimate we have is Q550. Rojner aggregated estimate across North Africa and the Arabian Peninsula. So we're looking at a subset of the 550 TCF of gas in place. By comparison, we've shown Europe, the estimate was made for Europe, it's 550 TCF. There's not many other estimates that have been published, and there's one or two snippets of information in the press. For example, I think OMV in Austria have estimated that the Vienna Basin potentially contains around 300 TCF of gas. There was an estimate prepared for Holland, basically, which had about 4,000 TCF of gas in place. So the indication is that Rojner's original estimate basically was conservative, and bigger numbers are likely to materialize. We've had a go at quantifying the resources basically in the region, and we've tried to take a bottom-up approach. So we've basically gone through all the basins in North Africa, including the 21 or so that sit in Morocco, and have basically identified the hot shales within those basins. Made an attempt at calculating the gross rock volume of those shales largely from public data, and there's an awful lot of public data basically on North Africa. In order to try and come down to a sensible estimate, then we've applied some criteria basically to constrain that estimate. And a number of criteria showing here. First of all, we put a depth limit on it. We said that anything less than 500 meters is simply either technically not achievable, would impinge on groundwater resource issues. Fracking, for example, probably at shallow depths would be horizontal and so very inefficient. So anything above 500 meters will be excluded. And for the moment, we've taken a commercial basement at 5,000 meters. So anything deeper than 5,000 meters, we've tried to exclude as well. So we're operating in that window. The Silurian shales, or any of those shales, of course, are made up of relatively lean organic shales plus some high gamma ray hot shales. And we've only calculated volumes for the hot shales. So we've specifically set a criteria, a limit of an API of 150 if we've got log data, or if there's any TOC data. Generally taken only include shale that's got a TOC of more than 1%. The other two important criteria were thickness. From our review of North American work, we came to the conclusion that probably about 50 feet was probably the minimum that you would consider, so about 15 meters in terms of thickness. Anything less than that is certainly uneconomic and probably technically not feasible. And the final criteria basically was to try and identify that shale rock volume that had been buried sufficiently deeply to have gone into the gas window, and we've taken a vitrite reflectance limit of 1%. So that's the gross rock volume. The other important element, of course, is trying to assess, well, what's the gas content of that gas rock volume? And I have to say we don't have any data at all. So as far as I'm aware, certainly no publicly available data in terms of gas content measurements of Silurian shales in North Africa. So we've basically then had to fall back to some analogy. And what we've done is we've built a rather simple empirical model, basically, that combines an illite isotherm with a kerogen isotherm and a gas porosity model, basically, to try and develop a mathematical way, at least trying to account for the potential changes in gas content with depth or with TOC or with porosity or illite content. And it's very crude, and it's based on typical TOC data measurements from the States. So that's all we've had to go by. But at least I think two things. First of all, it does constrain the gas contents, and when without just taking typical values from the United States and plugging those into the model, we actually come up with values that are very sensible and quite very similar to the shale gas contents that have been reported for the United States. And here are just a couple of graphs showing how the model would predict the change in gas content, expressed here as cubic meters of gas per cubic meter of rock, as a function of depth, as a function of total organic content, and a function of porosity. So very crude and simple, but at least it gives us a way of trying to allow for differences in gas content between different basins, to take into account changes in for example, changes in temperature. As the temperature goes up, the absorption capacity goes down. The non-ideal behavior, of course, or the gas law, of course, dictates that the gas content goes down as well. So we've tried to factor that in. So starting at the headline number, so the number we calculated basically for North Africa, so that's running through from Morocco all the way through to Egypt, plus Jordan, Syria, Lebanon, Israel, is a number of 5,250 PCF of unrisked expected gas in place. There's a huge range of uncertainty on that. So that's an expected unrisked number. If we compare that with Rojner's estimate, so the estimate, the nearest estimate we've got is 2547, but that includes North Africa and the Middle East. So we're definitely significantly higher in terms of the potential gas in place. So that looks really good. Lots of gas in place. So now a reality check. Sorry, I'll just quickly go through the distribution of that gas in place. That's the other interesting thing, of course, is that the largest potential gas in place sits in Algeria, and most of that sits in the Silurian. And so of the 5,250, nearly 4,000 TCF of unrisked gas in place sits in Algeria. And there's some very significant basins there. Basically, there's the Elisi Basin, the Kadams Basin, that extends into western Libya and in Algeria. However, the other countries have some significant potential, and Libya came out relatively low, and that's because some of the basins like the Kufra and so on probably don't have organic shales, or certainly don't appear to have gone through the gas window. But some of the smaller countries, Tunisia was quite interesting because the southern part of that of the country basically extends into the Gadam Basin. There's been a few wells drilled there where shale gas, hot shales of 35, 40 meters have been found. So Tunisia has some potential. Jordan we've talked about. We're trying to quantify the resource that comes out to around about 100 TCF of potential gas in place. Syria, a lot of the Silurian is missing over a large part of Syria. It's probably only present in the northeastern part of the country and in the area that is adjacent to the Jordanian border. So Egypt, Lebanon, and Israel. Egypt, for the reasons we talked about before, we think has very little potential because of either the non-deposition or the erosion basically at the Hercynian conformity, or a fascist change. So the shales, if the Silurian shales, if they are present, tend to be more silty than elsewhere. Lebanon and Israel, we couldn't find any evidence really for any obvious shales present, hot shales present in those two countries, though we did find a report that some Silurian hot shale have been found in a well drilled in Israel, but we've not seen the results. So that gives you a rough idea of the distribution. And the lion's share of this sits in Algeria, which is quite, maybe not unexpected. Okay, now the reality check. So the fantastic quantities of gas potentially in place. But the important thing to look at is, well, what's the concentration of that gas in place? And a good measure, of course, is the quantity in a square mile. And in all the areas we've looked at, so all the basins basically, in some cases aggregating the Silurian plus the Devonian, we've ended up with a range of around about 15 to about 40 BCF per square mile. And the Barnett, at least the latest public data we could find, basically some interesting recent papers, quote values around about 50 to 200 BCF per square mile. Now they're much more recent estimates than some of the more publicly quoted references. The interesting thing is that compare that with just some maybe well-known gas fields. So Uruguay, for example, in West Siberia, has around about 120 BCF per square mile. And the Le Mans field in the North Sea, which probably many of you know, 150 BCF per square mile. So the Barnett Shale is actually a really good field, and it's maybe a bit of an exception in that case. It's not surprising they've developed it economically because it's as good as some of these major gas fields at the moment. And we've got a problem here. So our gas concentrations in this enormous area we've looked at, which is, I don't know, 10 million square kilometers or something, is very, very small. Another way of expressing that was to build ourselves an a generic economics model that to try and tease out, well, what sort of gas volume per square mile do you need to make a commercial gas play? And of course it's a function of depth, because drilling costs go up with depth, function of gas price. Now we've taken a generic model for North Africa and the Middle East. We've put in typical generic well costs. I think at a 2,000 meter depth we were using about $4.5 million for a horizontal multiple frac well. We've been probably pretty conservative on the gas recoveries. We've taken, I think, between 0.7 and 1 BCF per well, and typically about 1 million cubic feet per day is the well potential. So that was based on a review of typical shales, not just the Barnett in the US. We've plotted on here some of the gas concentrations from the public literature in the States. And so some of these very shallow Paleozoic plays and the fallen basins of the Appalachians basically have quite low concentrations. The Barnett is sitting up here. Basically, this was an old public, an old piece of information from an old paper, but more recently they're quoting values of around 50 to 200 BCF per square mile. In order to make a shale gas play economic, then we think at a depth around 2,000 meters, then at a gas price of $300 per thousand cubic, it's about $8 per MCF, that you need around 30 to 40 BCF per square mile. And you can see that many of the areas that we've looked at don't meet that criteria, don't come to that criteria. There are a few exceptions, and there's that little collection of points there. So in some parts of the Elisi Basin in Algeria, the southern part of Tunisia, in the Khadams of the Burkina Basin, and western Libya, the shales appear to be sufficiently thick, basically, to start giving yourself a gas in place of about 40 BCF per square mile. So potentially, with the right fiscal conditions, then that might be a potential target. Of course, I think the other thing I should add to my model, or the economics model here, is that we assumed about a 50% government take. So of course the fiscal terms in Algeria are far more severe than that. But it's very instructive. So it thinks there's a real challenge here in terms of being able to develop what appears to be a very large resource base. You definitely need sweet spots. And as a rough guide, you probably need sort of hot shales that probably, in excess of 40 to 50 meters thick in this region. Europe might be different. We haven't got around to doing this sort of analysis yet. So just to finish off, so the region definitely has considerable shale gas in place potential. The Paleozoic clearly is the most promising targets because they're not only organic rich shales present, but they've also gone through a suitable burial history. They have sufficiently high maturity in places, and they've been uplifted in places to relatively shallow depths. So the Silurians are obviously the prime target, but there are other Paleozoic formations, so the Devonian, the hot shales, and the Frasnian. The Ordovician is locally prospective or locally contains organic rich shales, and possibly the Carboniferous as well. Our estimates of expected unrisked gas in place, 5250 TCF, so that's a significant increase compared to previous estimates, and is in line with the sort of findings of some of the other published information on gas in place in some of the European shales. The gas content in the area, however, appears to be low, so the order of 15 to 40 BCF per square mile. That compares with much higher values for the Barnett. I should add that it's not a totally bad picture because, of course, our estimates have been based on the organic rich shales, and there's a whole hundreds of meters of organic lean shales above the basal hot shale that could potentially contain some gas. I think some of the estimates in the States have been roughly assuming that these grey shales contain about 1/5 of the gas content of the deeper organic rich shales, and of course they're about 5 times as thick. So there's potentially another as much gas again that's in some of these organic rich lean shales. We think you would need about 30 BCF per square mile to make something commercial, and that's even being quite optimistic. You need an improvement in drilling costs and definitely much better fiscal terms for some of the countries we've looked at. In terms of ranking of opportunities, then those areas seem to stand out as the highest potential. The Licia Basin, Algeria, Khadams, in Tunisia and Algeria, and potentially Jordan, if you get the right fiscal terms and conditions and could aggregate up more the hot shales present there. Interesting that if you estimate the unrisked recovery from those, in just those most promising areas, then it comes out to be about 285 TCF. And that's interesting, that's about 5% of the gas in place calculation. And it's interesting the two estimates we've seen in the public domain for the two European basins, so the OMVs in Vienna and the Dutch and Holland. Also, they're coming out with recoveries in the best areas around sort of 5% of the calculated gas in place. So we're not miles out in terms of the relative proportions there. That's all I've got to say. If there are any other questions, I'd be happy to try and answer those.
I've got a question for you. I'm interested that in your predictions you're only considering thermally mature gas. The USGS study that Curtis published talks quite a lot about biogenic gas produced by bacterial activity, post-glacial. Now, if you do allow that in your estimates, that increases your possibility, your recovery. But in particular in Jordan, the water in the sands underneath the potential shale gas horizons on isotope dates are about 1 million years old.
Okay, possibly. Yes, yeah, it's definitely. Yeah.
Thank you. Do you not?
I guess I'm not an expert on biogenic gas, but the assumption we've made is that this is all thermogenic gas, and that the biogenic gas would probably only occur at shallower depths. We've excluded the top 500 meters, but maybe there's some potential upside, but I would not expect it to be significant.
I'll just offer a quick comment on that, if I may, Stewart.
Yeah.
I think one of the reasons that Curtis emphasised so much the biogenic aspect was because he spent quite a lot of time looking at the Antrim. And as we mentioned in our talk, the Antrim is probably the one area where biogenic component is significant. I think if he was doing his study again today, I'm not sure he'd emphasise the biogenic quite as importantly. I think it's an exception. I don't think it's a general rule.
Over there.
I remember the Al Jaffa area because I think BP drilled a well there in the late 80s, not one of its most successful ventures. It was completely immature. I do remember there was a very good source rock, but it was
in Jordan, the southern part of Jordan.
Yeah, how did you do
immature.
Yeah.
Actually, if you see the reference we've often referred to as Lunnings has done a very good analysis basically of many of the shale gas, the Silurian shales around throughout the region, and has published some maps basically that show the thermal maturity of the shales across Jordan. And you're right. I mean, the southern part of Jordan basically the shales are immature. It's only when you step across into the northeastern part of the country, near the Risha gas field, basically, that you get into apparent Petrenel reflectances of more than one. So
and just one quick one. These are all oil-prone source rocks, so I guess for them to be producing gas, they will, by definition, have been through the oil window. So, so I suppose what's happened to all the oil, and is there something special about the expulsion history of the hydrocarbons in these source rocks, which, because actually what I've noticed about none of these shale gas basins are really oil plays. There's not a lot of reservoir oil relative to the oil, the gas resource. So is there something about the expulsion history? Does the oil have to be trapped in the source rock and then get converted into gas?
Again, I can't. I'm not an expert. My geologist is not here at the moment. But in terms of the oil generation, of course, the shales in the Silurian have gone through the oil window. There's been a prolific expulsion of hydrocarbons, which of course provide a lot of the more conventional resources in that part of the world. So, I mean, I think equally, basically, as there's a very clear association between some of the gas fields, for example, in the Licia Basin in the Ordovician and the thermal maturity of the Silurian that sits above it. So, I think looking at the conventional resources gives you some confidence that the shales themselves have gone into the gas window. As an example, for example, in Jordan, the Risha field is clearly it's a relatively dry gas Ordovician field, basically, and has presumably been sourced from the overlying Silurian.
Okay.
I don't know if that answers your question, but not quite. Okay.
One more question, and then we need to move on.
Given that you need 4 to 8 million gallons of water to frack one of these wells, have you looked at the cost and practicality of accessing that volume of water in the Sahara?
Or anywhere?
Yeah. I think the answer is no. I mean, we've not accounted for that specifically. I mean, our cost estimates are for level 1, level 0 cost estimates. We've not gone down into scoping out the number of water supply wells you need to drill to supply salt water for the fracking operation. So the answer is no. But it's another, I wouldn't say nail in the coffin, but it's another significant cost